let's get started. So I didn't get a chance to release the new homework. It is going to be released today, and it's going to be due next Wednesday. Okay, so going back to Wednesday still. So still more than a week for you to finish the homework. Because this is because we were actually, I mean the homework 7 basically has already covered most part of until 5.4. So the new homework is going to contain some rest of the topics in 5.4, 5.5, and also some in the chapter 6.1. Okay. So today we'll be first finishing our discussion to Fourier services. Okay, and then we'll be starting our our discussion to the Poisson equation. Well, actually so Laplace equation and the Poisson equation. And the reason is that previously we have been mostly focusing on the one-dimensional scenario. Okay, and by introducing the Laplace equation and the Poisson equation, we will be getting from one dimension to one spatial dimension to 2 or 3 or 4 spatial dimension, because the latter are much imperfectly used in the physical world, because we live in the 3D or 1D. So again, let's first finish our discussion for Fourier services. Last time we have talked about the first part of 5.5, which is the completeness. Okay, although the title is completeness and the Gibbs phenomenon, actually we will not be reactively talking a lot about Gibbs phenomenon. It's an interesting reading material for you folks you're interested in, but it's not that much important in this class. So again, so what we exactly proved. So we started from 5.5, and what we have exactly proved was the first part was the pointwise convergence. Okay, pointwise convergence for classical Fourier series. Okay, or more specifically, the full, or more that points to the full Fourier series. Okay, on negative pi to pi with periodic boundary conditions. With periodic boundary conditions, and you might instantly ask that we have dealt with so many different boundary conditions, right? Including the Dirichlet, which will homogeneous Dirichlet, which will involve the which will involve the Fourier sine series, and the homogeneous Newman boundary conditions, which will involve the Fourier cosine series. Okay, why these two things are not discussed here? Well, the answer is that to maintain the neatness of the proof. Okay, this is something what we can only do right now. Okay, so actually it's not so hard to derive a similar proof, okay, for other types, okay, for other types of Fourier series and with the corresponding boundary conditions. But the periodic one is the most natural one to deal with, okay, and we will be actually for 5.5. Although we have stated, the convergence, the 3 different convergence theorems are stated in a much more, much broader way, okay, than the full Fourier series only with the periodic boundary condition. But for most of the materials in 5.5, we're only able, or actually to make this type of discussion to be concise. Okay, where we will only be discussing the specific proof, the rigorous proof. Okay, for the full Fourier series with the periodic boundary conditions. Okay, and again, the reason for us to do this, is to make it concise, to make our proof concise. Okay, and what you're going to see slightly later, which is that when we are talking about the full Fourier series, okay, with a periodic on certain interval with a periodic boundary condition, then actually the requirement for the different convergence theorem can be slightly looser than before. Okay, this is because the full Fourier series with periodic boundary conditions, they are the most regular ones. Okay, they are the most regular. Okay, so again, so what? This is what we exactly proved. We started from. Let me just use about 5 minutes to go through the most important steps, because the next part, the next topic that we're going to talk about is the proof for the discontinuous functions. Will be completely based on the proof that we presented last time. So what do we do? So we first of all, let's say we first do the Fourier. We first compute the Fourier series, which is that we starting from a periodic function fx, where x is between maybe pi to pi, and my fx is actually a C1 function on maybe pi to pi, which means that it has continuous, f is continuous by itself, and f has the continuous first order derivative. Okay. So the Fourier series for fx is something like 1 over 2a0, and then plus the sum from n equals to 1 to infinity, an cosine nx, and then plus bn sine nx. Okay? And our goal is to show that for any choice, okay? Our goal is to show that for any choice of x, okay, for any choice of x. Okay, again, our goal, the goal is that for any x, okay, for any x, then I'm having that the sum, okay, when I'm summing from 1 to n, the big N, okay, an cosine nx and then plus bn sine nx. Okay, this guy, it will converge, well, better for me to, okay, fx. When n goes to infinity, okay, this will converge to fx. So this was the goal, right? This was the goal. And the first step was that, okay. So first of all, these Fourier coefficients, they can be directly written into. We know, I mean, these are computed from the inner product, right? So the Fourier series is the Fourier coefficients. A and B and they correspondingly equals to integration from maybe pi to pi, fy cosine my, okay, 1 over pi, and then dy. Okay, Bn equals to 1 over pi from maybe pi to pi, and then fy sine my dy. Okay, and then by putting these two things back to the formula above, then we will obtain something like, okay, we'll be obtaining something like, okay, so let's say this is defined as fn x, okay, this is defined as fn x. Then my fn x is something like from maybe pi to pi, and then 1 plus, okay, 1 over 2 pi, 1 plus 2, and the sum from n from 1 to infinity, cosine my cosine nx, and then plus sine my sine nx, okay, and then fy dy. Okay, this is going to be my fmx by considering the integral form, okay, of the every Fourier coefficients. Then, because this guy is essentially cosine n y minus x, Therefore, we could define a kernel function. Actually, the kernel function kn, let's say knx, which equals to 1 plus 2, the sum n from 1 to n cosine nx, okay, and then my my fnx is exactly the same as the convolution between fy, okay, and kn. Sorry, fx and kn. Fx and kn. Well, 1 over 2 pi. Okay, and the kn is called the Dirichlet kernel. Yes, the same Dirichlet. This is the same Dirichlet that we have been talking about. Okay, the kn is the kn is the famous Dirichlet kernel. Okay, again, it's a kernel function. It's a kernel function defined on defined on negative pi to pi. Okay, and therefore the convolution. Okay, this convolution is considered. Okay, is considered only on negative pi to pi. Okay? And our goal was to prove that 1 over 2 pi multiplied by knx, okay, is essentially the delta function. Delta x, well, actually delta x, but defined negative pi and pi.
Professor.
Okay. Yes, you have a question.
I just think that infinity should be capital N for the f sub nx in the function.
Sorry,
You should take summation from small n equals to 1 to small n equals to capital N.
Yes, you're right. Here. From 1 to n. You're absolutely right about that. Okay. And our goal was to show that if we could prove that, okay, if we could prove that this kernel function is essentially the same as the delta function, okay, then we're done, right? Because everything convoluted with the delta function is exactly the same. Okay, then my fn, this is not equal to, but the limit when n goes to infinity. Okay, when n goes to infinity. Therefore, when n goes to infinity, the convolution kernel is approaching delta x. Then this is going to be approaching, my fnx is approaching fx convoluted with the delta function. Then the left side is going to be fx itself. Okay. Then we can prove that my fnx, okay, my fnx converge to fx. Okay, but how to do that? Well, first of all, we can directly. First of all, okay. So this was the let's say this is my step 1. Okay. I'm sorry. Step 1. The step 1 is to write everything. Okay, write everything in the kernel stuff. Okay. And then the step number 2. Okay. The step number 2 is to look for an analytical formula for the Dirichlet kernel. Okay, and by considering that cosine nx is essentially e the I nx and then plus e the negative I nx divided by 2. Okay, by doing this, we can finally find that the knx can be exactly represented as sine, okay, big N plus 1/2 x, okay, and then over sine 1/2 x sine x over 2. Okay, this is the analytical formula for the Dirichlet kernel. For the Dirichlet kernel. And this is the step number 2. This is the step number 2, and yes, and the next step, okay, the step number 3. Okay, the step number 3 is that, okay, by substituting this back to the convolution, then what we're actually obtaining is that now my fnx, okay, my fnx is essentially, okay, from the negative pi to pi, and then knx. And then my f, okay, x minus y, okay. You know what? Actually, sorry. This actually should be kmy. Convolution, right? Kmy, and then fx minus y. okay, and then dy and then over 2 pi. Okay, this is my f and x. And since we're having that, the integration, okay, the integration of knx dx, x from negative pi to pi, since the integration of this is exactly 2 pi, okay, since the integration of this is exactly 2 pi, then actually my fx, okay, my fx can be written as 1 multiplied by fx, which can be written as 1 over 2 pi, okay, and the integration from negative pi to pi, and then k, and let's say kmy dy, okay, and then multiplied by fx, which if I put the fx into the integral, although it doesn't do anything, this is going to be 1 over 2 pi from negative pi to pi kny, okay, and then fx dy. Okay, and now this is my f and x, this is my fx. So, because if I wanted to show that f and x approach fx for any choice of x, therefore I just need to show that their difference goes to 0. So my f and x minus fx, by subtracting the right hand side of the 2 equation, then I obtain from negative pi to pi, okay, kmy, this is a common factor, and then fx minus y, and yes, and then minus fx, okay, dy over 2 pi. Okay, and now since I already know what is the analytical formula for the dirichlet kernel, then I can simply rewrite it as negative pi to pi, and then sine m plus 1 over 2 x, y over sine y over 2, and then here, okay, fx minus y minus fx, okay, and then dy over 2 pi. Okay? And by combining these two things together, okay, combining these two things together, let me define a gxy, okay, gxy as a fx minus y minus fx over sine y over 2. So gxy is a function about y, but with a parameter x. Every time that I choose a fixed x, then gxy is only the function about y. Okay? And since so that means that my step number 4 for my step number 4, okay, step number 4, I found that fnx, okay, minus fx, now it becomes the inner product between sine m plus 1/2 y and then gxy. Okay? Don't forget, I wanted to show that the left-hand side goes to 0. I wanted to show that when the larger m becomes larger and larger, the left-hand side goes to 0. So left-hand side goes to 0, that is equivalent to the right-hand side goes to 0. But why the right-hand side goes to 0? Well, this is because that, first of all, the right-hand side, the inner product between gxy and the sine m plus 1/2 y, that is exactly, okay, that is exactly the Fourier coefficients. Okay, this is exactly the Fourier coefficients. This is actually equals to the Fourier coefficients. Okay, the Fourier coefficients. Actually, the nth Fourier coefficients for series as sine 2k plus 1 over 2x. Oh well, y. It doesn't really matter over here. Okay. And as we have shown that this is actually the Fourier series for what? This is actually the Fourier series for a very specific type of boundary conditions, which is that the f0, okay, equals to 0, and f prime pi, okay, equals to 0. Right? This is a Fourier series for a very specific type of boundary conditions. Okay? And according to the Bessel's inequality, okay, according to Bessel's inequality, okay, according to the Bessel's inequality, I'm having that the an, okay, the an square, the sum, okay, m from 1 going to infinity, 1 to, let's say 1 to n, okay, an square and the integration, okay, from a to b, and then the xn square, okay, and then dx, okay, this is actually smaller or equals to the smaller or equals to the so let me see what does the okay, from the integration okay, from a to b, okay, fx squared dx. Okay, the right hand side is, this is actually the square of the L2 norm of fx. Okay, the left hand side, this is the, well, okay, so actually in our case, why don't I just simply write it down? Why don't I just simply write it down as, okay, let's say gxy, okay, and then dy. Okay, so this now becomes the 2 norm. This now becomes the 2 norm of, okay, gxy. Okay, and my xn is essentially the sine, okay, 2n plus 1 over 2 x. Okay, and the an over here is exactly this. Okay. Fourier coefficients, the 2 norm of every basis, and the 2 norm of our target function itself. Okay. So the Bessel's inequality tells us that when we are doing the Gram-Schmitz orthogonalization, of course the square of the 2 norm, okay, the square of the 2 norm, okay, of every the square of the 2 norm of every decomposition, okay, sorry, the sum of the square of the 2 norm of every decomposition, okay, should be smaller or equals to the 2 norm of the function itself. Okay, should be smaller or equals to the 2 norm of the function itself. Okay, so that tells us that so step number 5. Okay, step number 5. As long as my gxy, okay, my gxy is a L2 finite, function, okay, then we can guarantee that my an, okay, will converge to 0. Then we can guarantee that my an is going to converge to 0. This is because what you're going to find is that the 2 norm of the xn, okay, is actually a fixed number. It doesn't depend on the choice of n. It doesn't depend on the choice of n. And my an, okay, then my an is going to converge to 0. If my an converges to 0, then that means that my fnx minus fx, that this will also converge to 0. Okay? But everything depends on if my gxy, okay, has a finite 2 norm. Because if it doesn't have a finite 2 norm, then this right hand side is infinity. If the right hand side is infinity, then you cannot say anything, okay, about the left hand side. You cannot say anything about that side. It can be anything. Right? Okay. So everything depends on that my gxy has a finite 2 norm. But what is that? Okay. What you can see is that, okay, the gxy, the square of the 2 norm for that is actually the integration from negative pi to pi, and then fx minus y, and then minus fx, okay, over sine y over 2, okay, squared dx. You see, it is exactly because my f is not only continuous, but also has a continuous first order derivative, then we know that, first of all, my gxy is continuous everywhere. Okay? This is, and also, okay, and also when y goes to 0, my fx minus y minus fx, okay, over sine y over 2, this is actually 2f prime x, right? This is according to the L'Hospital principle, right? Okay. So, which means that my gx y, this guy, okay, is integrable. Okay, integrable, which will finally guess that the gxy square of the 2 norm, okay, is finite. Okay, is smaller than infinity. Okay, so we have spent, well, I hoped 5 minutes. I actually spent 20 minutes, okay, to make the review. Okay, so is there anything unclear for this procedure? Okay, I mean, this is complicated enough, right? This is complicated enough that, first of all, it has to be divided into 5 steps. And then second, actually, it involves a lot of related messages that we'll be discussing, okay? And there are a lot, and again, there are a lot of technical details. So you should figure everything, you should try to figure everything out by yourself, okay, without my help, okay? Then you'll be familiar enough with that and obtain a deeper comprehension of everything right here. Okay? And I would like to, and don't forget, what was that? This is the pointwise convergence for the classical Fourier series, and especially for fx to be continuous, and to be fx to be a C1 function. C1 function means that again it is continuous, and not only continuous but also has continuous first order derivative. Okay, and what did we state? Okay, what did we state previously for? Okay, so then the second part. Okay, second part. The pointwise convergence for pointwise convergence. Okay, for discontinuous functions. Which is that now my fx, again, it belongs to from degree pi to pi with the periodic boundary condition. Okay? From degree pi to pi, and however, my fx, both my fx and f prime x are piecewise continuous. Okay? They are piecewise continuous, and for convenience, let's just say that they are having finite, both fx and f prime x, they're having finite. Okay, they are having finite many of discontinuous point. Okay, with, let's say, with finite discontinuous point. Then the Fourier series, okay, again the Fourier series, let me again quoting the fnx, okay, fnx. The Fourier series that should converge when n goes to infinity. Okay, the Fourier series that should converge, always converging to 1/2 of fx plus and then plus fx minus, where the fx plus and fx minus are the right limit and the left limit, okay, for fx correspondingly. And again, if fx is continuous at a point x, then my fx plus and fx minus, they are exactly the same thing, okay, which is fx itself. Then 1/2 of 2 times of fx itself is fx itself. There's nothing wrong about it. In one, let me finish this two. And if on the other hand, if x is exactly the discontinuous point, okay, if x is exactly the discontinuous point, then the right limit and the left limit is very likely to be is going to be different. Okay, it's going to be different. And the pointwise convergence for the discontinuous function now tells us that instead of converging to either of them, then actually the Fourier series for the function fx, okay, actually converges to the midpoint of the definite limit and right limit. Okay. Now, do you have any question, Ethan?
Well, Professor, I'm just asking, is that x is between minus pi and pi, or is it f(x) is between?
Actually, the x can be negative pi or pi.
Is that the boundary for f(x)?
Because this is because again, okay, this let me try to put it this way. This is because now we are talking about the periodic space. We're talking about periodic space. So what you are seeing in the interval from negative pi to pi, okay, due to the periodic boundary condition, actually it is actually completely legal for us to glue the pi and negative pi together. Okay. So now we're actually looking into. So why don't we consider an angle? Okay, a space of angle for that. Okay, the space of angle. So a space of angle starts from 0 degree. Okay, and then it ends. So from the positive part, it ends at pi, right? From the negative part, it ends at negative pi. But negative pi and pi actually are the same thing. Okay, for a periodic space. Okay, for a periodic space. Then you may ask the question that what if the function is not exactly periodic? For example, it starts from, let's say it starts from 0, but it ends 1. Okay, what does that mean? Then this function, again, this function is again, although this function seems to be continuous, okay, for every point within negative pi and pi, but, okay, this function is actually a discontinuous function with one discontinuous point exactly over here. Because here, on this direction, it approaches to 1. It approaches to 1. And on this direction, it approaches to 0. Okay, so so with the idea of a periodic space, okay, this function is still discontinuous. This function is still discontinuous. And it has only one discontinuous point, which is exactly on negative pi or on pi. Okay? So, yes, so this is what we are going to prove. And what we are going to, and the procedure, okay, the procedure is we are actually going to exactly copy the procedure number 1 and the procedure number 2, which means that we have already obtained that my fnx, okay, my fnx equals to 1 over 2 pi, or 1 over 2, yeah, actually 1 over 2 pi, okay, 1 over 2 pi fx, and then convoluted with the derivative kernel knx. Okay, and now since our goal is to show that fnx, okay, converges to the midpoint of the converges to the midpoint of the left limit and the right limit of fx at the point x, then actually will be instead of being interested in the difference between fnx and fx, we are actually more interested. Okay, our interest turn to the difference between fx and the midpoint itself. Okay, fx plus and fx minus. How is this expressed? Well, how is this expressed? Well, this actually can be expressed as follows. Okay, this can be expressed as follows. So first of all, okay.
Professor,
Yes.
You wrote fx belongs to negative pi to pi. I guess it should be x belongs.
Yes, you're right. So my fx is you're right about this. Yes, thanks for catching the typo. Okay. Well, we'll be using a very similar way for us to express the fx plus and fx minus. First of all, don't forget our goal is to show that the limit of n goes to infinity, okay, the limit of this guy goes to 0. Okay, this is our goal. And again, don't forget my fnx equals to from negative pi to pi, kny, okay, kny, and then f, okay, x minus y x minus y, and then minus fx d y, okay, over 2 pi. The question is, how do I express 1/2, okay, fx plus, and 1/2 fx minus? Okay, the question is these two things. Well, you see, the fx plus and fx minus, okay, both of them can be written into, okay, so let's say fx plus, okay, and then multiplied by 1/2, right? I'm basically doing nothing, and the 1/2, you see, we already know that the Dirichlet kernel, okay, the Dirichlet kernel, the integration of the Dirichlet kernel actually is what? It's actually 2 pi. Okay? And the Dirichlet kernel is made up by what? The Dirichlet kernel is made up by all by cosine functions, which means that the Dirichlet kernel is essentially a what? A even function. Okay? That means that the integration of the left half of the Dirichlet kernel and the integration of the right half of the Dirichlet kernel should be exactly what? Should be both exactly pi. Okay? They should be both exactly pi. Therefore, this can be written as, okay, let's say 2 pi over pi, which now becomes, okay, now 1 over 2 pi fx plus, and then multiplied by the integration from 0 to pi, not from negative pi to pi anymore, okay? From 0 to pi, and then the Dirichlet kernel, kmy dy, okay? Or for me to, I can just simply put the, I can simply put the over 2 pi over here. And then fx minus pi over 2 pi, which is the fx minus, okay? Now, I'm going to do from negative pi to 0, and then kny dy over 2 pi. Okay, so that's good. I'm just playing an algebra trick. Okay, I'm just playing an algebra trick. Here, the negative 2 pi is over 2 pi is over here, and the pi itself is written as the half integration. Sorry, the integration of the right half, or the integration of the left half, okay, of the Dirichlet kernel. I'm not changing anything. Okay. So now the fnx minus 1/2, okay, fx plus, and then plus fx minus, okay, this guy now can be rewritten, okay, now it can be rewritten into the difference between these three intervals. Or more specifically speaking, if I propose, okay, to split this integration, okay, into 2 parts, into from negative pi to 0, and then plus from 0 to pi, okay, for me to match the integration from negative pi to 0 and from integration from 0 to pi, okay, if I propose to do that, then what I'm going to have is exactly that, okay, the integration from 0 to pi, okay, kny, and then fx minus y, and then minus fx plus. So that's good. And this is the dy, okay, this is dy over 2 pi. dy over 2 pi. This is good? Okay, this is good. And second, okay. Well, you know what? Actually, I need to change I need to change the minus to plus over here. Well, it doesn't really matter. Okay, let me tell you why it doesn't really matter. This is again because the Dirichlet kernel is an even function. Okay, it's an even function. It's actually symmetric. Okay, it's actually symmetric. And actually, what you're going to see is that for well, you know what? I don't have to do that. I don't have to do that. I just need to do it slightly differently, okay, from what is being doing in the book. So, you know what? So now what I'm going to do, okay, this is fine. So now what I'm going to do is that I am going to change the integration. I'm going to manipulate the upper bound and lower bound of the integration a little bit. So now this is going to be from 0 to pi, and this is going to be from negative pi to 0. Okay, I'm changing this a little bit. Okay, so that later I will be able to continue to do my limit. Okay, you see, it's actually very interesting to do that. So now this becomes this part becomes from negative pi to 0, and then the second part is from 0 to pi. Okay, kny, and then fx plus here is still minus. Okay, and then minus y. Okay, now here is still minus y. Okay, and then minus fx minus dy over 2 pi. Okay, and I'm going to write down what is k and y. Okay, and I will be defining here it's from negative pi to 0, and then g. Okay, gx plus y, and then sine m plus 1/2 y dy over 2 pi, and then plus, okay, from 0 to pi, gx minus y sine m plus 1/2 y dy over 2 pi. And we need to define, what is gx plus and gx minus. Here, my gx plus y is exactly, fx minus y minus fx plus over sine y over 2. And my gx minus y is exactly fx minus y minus fx minus over sine y over 2. So you see, the step number 4 is going to follow. Step number 4 is going to follow that, you see, because now, again, don't forget, I would like to prove that my Fn goes to Fn minus 1/2 of the average, of the two-side limit is approaching 0. Okay, and now this is now be split into the two different integrations, and again each of the integration is actually a certain type of inner product, actually the weighted inner product. Okay, this is actually the weighted inner product. This is actually the weighted inner product between gx plus y, and sine m plus 1/2 y. Okay, let's say 1/2, and then plus 1/2. Okay, gx minus y, and then sine m plus 1/2 y. So you see, in order to show that this guy goes to 0, I would like to show that this guy goes to 0. Right? I would like to show that this guy goes to 0. And these two things, again, are exactly the Fourier coefficients. These two things are exactly the Fourier coefficients for gx plus and gx minus. Okay? And they will necessarily goes to 0 when n goes to infinity, as long as that I can provide that my gx plus y is L2 finite. On negative pi to 0, and gx minus y is also L2 finite. On 0 and pi. Now you are going to see why it is actually important for us to choose the right integration interval. This is because, again, this is my gx plus, this is my gx minus, right? And L2 norm, okay, it's L2 norm on negative pi to 0 is going to be, okay, from negative pi to 0, and then this guy square, and then dy. Okay? Same thing for this, okay? The L2 norm, okay, so I'm going to put a split in the middle, okay? And again, the square of the L2 norm, again, is going to from 0 to pi, okay? This guy square and then dy. So good? Well, why these two things are finite? Why these two things are finite? You see, when I am having y when I'm having y to be negative, x minus y is larger than x or smaller than x. When I'm choosing y, you see, what's the range of y for now? From negative pi to 0, right? When I'm choosing my y to be negative, is my x minus y be larger than x or smaller than x? Y is negative. Okay. My y is negative. So my x minus y should be what? My x minus y is larger than x or smaller than x when my y is negative. Should be larger than x, right? Should be larger than x. Which means that when my y approaches 0, my fx minus y is approaching x from the right side or from the left side.
From the right side.
Here again, I'm having, let's say, I am having a, let's say, here's a discontinuous. Let's say here's a discontinuous point. Okay, here's a discontinuous point. This is my fx plus. This is my fx minus. Okay. Now my y is smaller than 0. Smaller than 0. Okay. And I'm talking about fx minus y. I'm talking about fx minus y. The question is, where is fx minus y? Is that here or here? Is that on the right or on the left?
On the
right or left?
On the right.
Right. It's on the right, right? So here is my fx minus y. Right, here is my fx minus y. Because again, it's because my y is more equal to 0. Now, when my y approaches 0, my fx minus y is actually what? It's actually approaching my fx plus on the right side. Right? Which means that here, when my y goes to 0, okay, when my y goes to 0, actually goes from 0 from the negative side, then my fx minus y, okay, will equals to the limit of fx minus y will equals to fy star. Sorry, fy plus. Is it f plus?
I think
Yes.
it's at x plus.
You're right. You're right. fx plus. So is it good? Okay, and the same reason, when my y approaches, is always larger than 0, and approaches 0 from the right side, then my fx minus y, so now, where's my fx minus y? When my y is always larger than 0. My fx minus y is now on the left or on the right?
On the left.
On the left. Okay? So now, when my y is larger than 0 and gradually approaching 0, then my fx minus y is here, and approaching what? And approaching fx minus. Okay, fx minus. This again suggests that, okay, these two things, okay, are L2 finite. These two things are L2 finite. Because again, you see, first of all, when my y doesn't equal to 0, okay, when my y is away from 0, then this guy is what? Is a finite number. When my y is approaching 0 from the negative side, this guy has a limit. Okay, this guy has a limit. And since my f, it at most has finite many discontinuous points. Okay, then that means that this guy, no matter for what x that I choose, this guy and this guy, okay, both of them should be integral. since both of them are integrable, or let's say they're true finite, then that means that correspondingly their Fourier coefficients should approach 0 when n goes to infinity. Okay, these two Fourier coefficients should approach 0 when n goes to infinity. And yes, and this is so this is the so now this is the so this finished the proof. Okay, this finished the proof for the discontinuous functions. Okay, for the discontinuous function. And let me still cover the proof for the uniform convergence. Okay, so again, the proof for the uniform convergence. Okay, and can anyone tell me what was the requirement for the uniform convergence for the Fourier coefficients for an arbitrary symmetric boundary condition? What was the requirement for the uniform convergence? Okay, so what should exist at first?
First and second derivative.
Okay, so first the f prime, they should exist, and then what? Continuous, right? Okay. But again, this was actually what? This was actually the requirement for the uniform convergence for arbitrary symmetric boundary condition. Okay. Now, if we are again only focused on the classical Fourier series, okay, classical Fourier series. If we are focusing on the classical Fourier series, okay, which means that again, when we are talking about when we're talking about, okay, x belongs to from negative pi to pi, okay, from to pi with periodic, okay, with periodic boundary conditions. Actually, this can be the requirement, okay, can be loose. The requirement can be looser than before. So, which means that now again we only require that fx, okay, belongs to C1 from negative pi to pi with the periodic boundary condition, which means that, okay, periodic, which means that my fx, okay, exists, and my f prime x is also continuous. And has period 2 pi. Okay, what can you tell from this requirement and our requirement for the pointwise convergence? Well, you see here, our requirement, my fx, is a f1, is a C1 function. It is itself continuous. Its first order derivative is also continuous and has a period of 2 pi. Okay, and if we go all the way back, okay, if we go all the way back to the very beginning of this class, what was the requirement? What was the requirement for the pointwise convergence? Fx is continuous. Fx has a first order derivative, which is also continuous. They are what? They're actually identical. They're actually identical. Okay, they're actually identical. So it is adequate for us to say that. Okay, I mean, after we finish the proof for the uniform convergence, we can say that if we are talking about a very specific type of boundary condition, which is periodic, the periodic boundary condition. When we are talking about the periodic boundary condition, then the requirement that fx and f prime x, they are continuous, they exist and are continuous on negative pi to pi, or from negative L to L, or any other interval. Okay, this is adequate for both pointwise convergence and uniform convergence. Okay, but it is only in this case. Again, this is because the periodic boundary condition is actually it's actually a very strong boundary condition. It strictly requests, okay, the behavior of the function when we are approaching one side and another side. Okay? So again, if we're talking about a general type, if we're talking about a general type of the symmetric boundary condition, then we don't necessarily have this good property. Okay? And in that case, we will still be requiring the existence and the continuity of the second order derivative as well. But again, here we just simply need the first order derivative, and that is going to be adequate. Okay? Again, this only works. This simplified requirement, okay, for uniform convergence only works for periodic boundary conditions. Okay? And we are going to carry out the proof. And again, the Fourier series is fx equals to 1/2 a0 plus the sum n from 1 to infinity a n cosine nx, and then plus b n sine x nx. Oh, don't forget what we have already proved. We have already proved the pointwise convergence, right? We have already proved the pointwise convergence, which means that now I have the confidence, okay? Now I have the confidence to remove the question mark and then say, indeed, my fx equals to this. Okay, my fx indeed equals to this. For any choice of x, we have just proved it at the beginning of the class. Okay? It's now the problem that we don't yet know that what is the convergence speed for the different choice of x. Again, uniform convergence. Uniform convergence requires that the converging to regardless the choice of x that I choose, okay, the converging itself, okay, is uniformly bounded by the same upper bound. Okay, it's uniformly bounded by the same upper bound. Again, what is meant by uniform convergence? If you don't remember that, okay? Again, the uniform convergence. Let me write it down, right? The uniform convergence means that, okay, the limit of when n goes to infinity, okay, which is that the fn x minus fx, okay, not only this guy itself, but also the supremum, okay, for any x, the supremum of any x, okay, this guy goes to 0. Supremum, the maximum, well, actually in a closed interval, actually say maximum. Okay? The maximum of the difference for any choice of x, okay, this guy also converges to 0. This guy also converges to 0. And if you don't remember, the pointwise convergence doesn't necessarily mean the uniform convergence. Okay, the uniform convergence is much stronger than the pointwise convergence. Let me just say that. Okay. Now, what do we have? Well, you see, again, let's say what is the how do we compute? Okay, how do we compute an? An is again the from negative pi to pi fx, okay, cosine nx gx over pi. This is my an, right? Well, you see, this is again the integration of the product, okay, of two things. And of course, we can say that this is the inner product between fx and the cosine nx. On the other hand, since this is integration of a product, we can also consider doing something like integration by parts. Okay, we can also consider doing something like integration by parts, which means that I can simply rewrite this guy as from negative pi to pi and then fx. Okay, now d sine nx and then be divided by n pi. Okay, I'm going to do some integration by parts. So this is going to be, okay, first of all, fx and then sine nx over n pi, okay, be evaluated from negative pi to pi, and then minus the integration from negative pi to pi, f prime x, okay, and then sine nx dx over n pi. So far so good? So far so good? Everything is okay? I'm just doing an integration by parts for the Fourier coefficients, just doing integration by parts, nothing else. But you see, this guy's what? This guy is the Fourier coefficients for cosine nx, which is exactly the inner product between fx and the cosine nx. So that's okay. This guy's what? This guy is the inner product between f prime x and sine nx. So the outcome, okay, the outcome of this guy should be what? The inner product between fx and sine and cosine nx lead us to the Fourier coefficients an for f itself.
Oh.
Now, this is the inner product between f prime x and sine nx over pi. Of course, there's a scale O n, but I can extract it out. Right? I can extract it out. I can erase this n and then put it on the right. Sorry, and put it over here. Okay. So this guy, this inner product between f prime x and sine nx. Now this guy becomes, okay, it exactly becomes the Fourier coefficients, okay, the Fourier coefficients of, or let me just write it down as. So first of all, this guy is 0. This guy is 0. I don't have to stress that, right? This guy is 0. So now this guy becomes 1, negative 1 over n, the inner product between f prime x and sine nx. Okay. So now this guy is also a Fourier coefficient, but for what?
For the derivative.
For f prime x. And what Fourier, especially the coefficient of what term? For sine x, right? So due to our rules of the naming, let me call this guy to be a b negative 1 over n bm prime. What does it mean by bm prime? That actually means that I'm having f prime x, okay, equals to 1/2 a0 and then plus the sum m from 1 to infinity, okay, m from 1 to infinity, a0 prime, and then an prime cosine nx, and then plus bm prime sine nx. Okay, so this bm prime is exactly this bm prime. Okay, so that's good. My an, the Fourier coefficients, okay, the Fourier coefficients for f is actually directly related to bm prime, which is one term, which is the Fourier coefficients for what? For f, for the derivative, first order derivative of fx. Is okay? So that's okay. So I'm having, so to summarize, I'm having an equals to negative 1 over n bm prime. Of course, n cannot be equals to 0. I'm starting from n equals to 1. Okay. Same reason, bn can be written as 1 over n am prime. Okay, you can just try it by replacing the cosine nx to sine nx, and you'll be obtaining the same thing. Everything is the same, right? Integral by parts. Okay. On the other hand, we know that from the Bessel's inequality, okay, from the Bessel's inequality, okay, from Bessel's inequality, I know that the let's say, okay, so the integration, so actually that should be, yes, let's do this. The integration of a0 prime, okay, a0 prime from negative pi to pi, okay, 1 over 2 pi dx, and then plus, well, actually I should do this. I should do square, okay, and then plus the and then plus the 2 norm, okay, and then plus the 2 norm of let's say from negative pi to pi, and then a n prime square, and then multiply by cosine square nx dx over pi, and then plus from negative pi to pi bn prime square sine square nx, okay, dx for pi. This guy should be smaller or equals to, well, actually, here is the sum, okay, sum from m from 1 to n. Sum m from 1 to n, okay, should be smaller or equals to the 2 norm of f prime x, okay, which is the square of 2 norm. Sounds good? Sounds good? This is the best inequality. Well, again, what are the left-hand sides? The left-hand sides are exactly, okay, so the 2 norm, okay, the 2 norm of every single term. The 2 norm of every single term, which is the an prime square, and then the 2 norm, okay, the square of the 2 norm for cosine nx, okay? Bn prime square, the 2 norm for sine squared nx. Again, the sum of the 2 norm, the sum of the square, the square of the 2 norm of every single term should be smaller or equals to the square of 2 norm of the function itself. That's as okay. Well, I already know that my f prime x is what? My f prime exists and is continuous. It's a periodic function. What can I say about its 2 norm? What can I say about its 2 norm? Continuous function. It's a continuous function on a closing interval, and it's periodic. What can I say about its 2 norm? Is there any possibility that the 2 norm of f prime x is infinite? No. Because, again, it's well defined. It doesn't go to infinity. It cannot go to infinity on any single point because it's continuous and has and is periodic. Okay, it's continuous everywhere, including negative pi and pi. Okay, therefore it cannot go to infinity. So this guy, okay, is smaller than infinity. This guy is finite. Therefore, okay, because the integration of cosine nx and the cosine squared nx and the sine squared nx, okay, what we can find is that these things are exact constants, and actually they are the same constants. Okay, they are the same constants. Therefore, we will be able to derive that, okay, the sum excluding the first term. Okay, that's excluding the first term. Now the sum from 1 to let's say from 1 to infinity. Okay, from 1 to infinity. Okay, my an prime square and then plus the bn prime square. Okay, this guy is smaller than infinity. Is this okay? Again, the integration of cosine squared nx. Okay, that's a constant. It's irrelevant of the choice of my n. Okay, and the square of sine squared nx. Okay, this again is something that irrelevant of my choice of n. You have done this type of integration for many, many times. So I am able to say, okay, now, okay, the sum from n from 1 to infinity, okay, an, okay, cosine nx, the absolute value, and then plus bn sine nx, absolute value. Well, again, don't forget, if I just simply open the bracket, if I open the absolute value bracket, okay, then the sum itself is going to be what? The sum itself is going to be our fx. Okay, the sum itself is going to be our fx. I'm just simply adding the absolute value to the bracket for every single term to stress that this is going to converge, and actually absolutely converging. Okay? So this guy is actually, first of all, it's actually smaller or equals to the sum from n equals to 1 to infinity, okay, an, and then plus bn. This is because of what? This is because cosine nx and sine nx, they are at most 1. Their absolute value is at most 1. Okay? So the first inequality, of course, holds. And second, I already know how to express my an and bn. Right? My an are exactly 1 over n bn prime. My bn is exactly 1 over n an prime. So that is exactly n from 1 to infinity. Okay, 1 over n multiplied by bn absolute value prime and then plus an prime absolute value. So it's good. So it's good. Okay, and the next step, okay, is we are going to prove something that's called Schwarz inequality. Schwarz inequality. Okay, Schwarz inequality, which is that the sum, okay, the sum of AB, an, bn, okay, the sum of n from 1 to infinity, or n from 1 to, let's say n from 1 to n, okay, n from 1 to n. Schwarz inequality. This guy, okay, is smaller or equals to the sum, okay, the sum of an squared, n from 1 to n, and then multiplied by the sum of bn squared, n from 1 to n. Okay, n from 1 to n. This comes from something. This result is actually very close to the arithmetic mean is larger than the geometric mean. Okay, but you are not required. You're not strictly required to comprehend the Schwarz inequality. Just need to know that this is actually an inequality that's actually very commonly used, okay, everywhere in analysis. Okay, just to see that, okay, because well, actually.
Is there a
yes, there should be a square. There should be a square root.
square root?
Yes, very nice, very good catch. Okay. The thing is that what you're going to see is that the right-hand side has more terms like n squared, bn squared. Okay, and the left-hand side is actually combining everything. It's actually not hard. It's actually not hard for us to obtain, for us to accept something like, okay, an squared plus bn. Let's say a squared plus b squared is larger or equal to 2ab. It's not hard for us to obtain, to accept something like this, right? Okay, so the Schwarz inequality is a much more advanced version, okay, of this. Yeah. So let's just accept this, okay, and then move forward. So now this is going to be my an, this is going to be my an, this is going to be my bn. Okay. So by the Schwarz inequality, this will be smaller or equals to, okay, first of all, the sum, n from 1 to infinity, okay, 1 over n squared, 1/2 times, and then multiplied by n from 1 to infinity, and then n from 1 to infinity, and then an squared plus, an prime squared plus bn prime squared. Yes, here we go. And 1 over 2 times. Okay, this is smaller than infinity. Why this is smaller than infinity? Well, first of all, this guy, is this guy smaller than infinity? Is this guy smaller than infinity? The answer is yes. It's actually not so hard to show that. Actually, I think you have really learned that in calculus, right? The infinite sum of 1 over n is divergent, but the infinite sum of 1 over n squared, that is convergent. The second thing is the an prime squared and bn prime squared, everything combining up. But we have just already proved what? We have just already proved that this sum, okay, is smaller than infinity. This sum is finite. This sum is at most, okay, a volume, okay, of the two norm, the square root of 2 norm of fx prime. Therefore, this guy, for the right hand side, this guy is finite. This guy is finite. And this guy is also finite. Their product is, of course, finite. Yes, you have a question?
Professor, I think you need to put a coefficient 2 in front of the right side, because it's an prime plus bn prime as bracket square. So there's a 2 times an prime times bn prime.
Is that right? Is that right? Is that true? Let me think. Oh yes, you're right. You're right. You're right. You're right. Because yes, yeah, that's right. That's right. Because am prime is contributing one term of is contributing one piece, one copy of 1 over n squared. And bm prime is also contributing another copy of one and okay, 1 over n squared. So yes, you're right. So this is actually going to we are going to have a 2 over here. Okay, well, we have a 2 over here. Or 2 to 1/2 times. It can be either left on the left or on the right. It doesn't really matter. Okay, so that this results means that the Fourier series is converges absolutely. Okay, the Fourier series converges absolutely. And okay. First of all, the Fourier series converges absolutely. And let me see. So this again tells us that the Fourier series of fx, okay, converges absolutely. Okay, it converges absolutely. And also, we have that the maximum of, so now the maximum for any type of x, because you see, our goal was what? Our goal was to show that the upper bound between the upper bound of the difference between fx and fnx, okay, the upper bound of this should converge. This is the idea behind the uniform convergence, right? Okay. So this we have just shown that this actually equals to the maximum, okay, of x, because we have already shown that my fx exactly equals to the Fourier series, the infinite Fourier series. So this is the infinite Fourier series minus this is what? The finite Fourier series. So the difference is what? The difference is exactly the tail. Okay, the difference is exactly the tail. So this is going to be okay. So n from n plus 1 and going to infinity. Okay, and then an cosine nx and then plus bn sine nx. Right? So this part is completely close to each other. And then the next thing is that you see this is the absolute value of a lot of sum. This is the absolute value of a lot of sum. And the absolute value of the sum should be smaller because of what? The absolute value of sums of a sum should be smaller equals to the sum of every single absolute value. Right? So this should be smaller or equals to, okay, this should be smaller equals to the, again, taking x for the maximum, okay, now the sum of the absolute value, which is, okay, an cosine nx, and then plus bn sine nx. So far so good? So far so good? But what we have just shown, we have just shown that, you see, the sum of the absolute value, an cosine x, bn sine x, the sum of these absolute values is what? Is finite. The sum of a series of absolute value is finite. Every single term is what? Is non-negative. Every single term of non-negative. So the sum of the tail, you see, here is the sum from 1 to infinity. Here is the sum from n plus 1 to infinity, right? the whole sum is finite. So what can I say about the tail? What can I say about the tail of the sum? It can only become smaller and smaller and smaller and finally approach 0. Right? It can only approach 0. So the limit, okay, the limit when n goes to infinity, the limit when n goes to infinity, here the limit when n goes to infinity, finally this guy has to be 0. Okay, so here is the total proof. Okay, here's the whole proof, okay, for the uniform convergence. Okay, here's the whole proof for the uniform convergence. Let's take a 5-minute break, and then we'll be to resume at 45.
那个 Bessel's inequality 我们讲过吗？
不记得，应该是
因为我记得他上次讲这个的时候，他用的是那个 equality。
咋拼来着？咋拼的？你写了吗？不是。BESSEL。
我不确定。
OK。我不记得上面讲的。OK。
天哪，这么多！
十跟
书上是有，但他上次讲的是 equality， 我不知道他那个 Bessel's inequality 他有没有讲过。
所以如果真的到时候出了什么差错，收不到，那怎么办？